Science School of Computing to talk about algorithms for data analysis. So Jeff is an assistant professor in the School of Computing and director of the Data Management and Analysis track, which offers PhD, master's degree, and graduate certificate in big data. His work span algorithm, data mining, machine learning, and computational geometry, which focus on each topic on scaling to massive amount of data. He has a bachelor's computer science in computer science and math from Rice University and a PhD from Duke. He won the NS Career Award and previously held the NS Computing Innovations Postdoctoral Fellowship and USF Graduate Research Fellowship. He has been in China 4 times, including his wedding. So welcome.
Sure, yeah. So thank you very much for the introduction and for having me here. So I'm in, let's make this full screen. So I'm in the computer science department. So I'll try and explain what, again, my perspective on what big data is, but in particular, what are the algorithms and how do these apply to the analysis part, which, as you've been explaining, is a very hot area right now. And since I'm in the Department of Computer Science, I view this partially as from the perspective of teaching and training. And so I think when I'm training my students, what do I want my students to know so they can go out and do great work in research or in industry in big data? And I think of it as kind of the intersection of these different areas which have traditionally lied in computer science or in various other areas. This includes algorithms and data mining and machine learning and databases and statistics, and to really understand big data analytics and to kind of go out and be able to combine all these techniques together, you need these trainings. And I think someone who has combined all these together would be somebody you call a data scientist, right? So my goal as a professor is to train these data scientists and then go out and help you guys, like the other speakers, help do all this cool work in big data. So now the way I want to start introducing my view on why big data is important is thinking about how we've done science. Okay, so classically, how science has been done, and this dates back like probably at least 100 years back to like Mendel and people, is that you would start science by you make some hypothesis about the world, right? You think, maybe if if this gene is something that causes cancer or something like that, and then you go and you gather data about your patients, and then you kind of compute statistics on the data you've specifically gathered, and then you try and draw some conclusion based on these statistics. And sometimes this works, and you said, okay, I've discovered something new, but other times you say, well, this data did not support this, and you have to go back and make this new hypothesis. And you kind of repeat this process. This is the classic scientific paradigm you probably all learned in school at some point. We've been doing this for a while now, and this is not always how science is done now, and it's moving to a different way of trying to learn new things about the world, and that is because we've been doing this, we've gotten very good at gathering this data. It's now cheaper to store, it's easier to gather with different sensing technologies and everything. So now we start with this enormous corpus of noisy data. And I say it's enormous because we're very good at gathering and storing it, and it's noisy because this noisy can mean a few different things. One is we could have gathered it for one purpose, and now we want to analyze it for another purpose, right? So it's not exactly what we thought it was. Also, because we're gathering so much of it, we don't have time to check every little element of the data. We kind of just throw it in the database and then hope that when we look at it later, there's we start with this data, and then we kind of try and use some data squashing or something to get down to some working data. Maybe this is the stuff we think is relevant. This is something that fits in the computer that we're in the memory of our computer, so we can do some analysis on it maybe. And then we do data mining on this data, on the relevant part, what we think is relevant. And this is kind of the forming hypotheses and computing the statistics at the same time. Right, so you're kind of searching for the hypotheses which are statistically valid. And then if you find something, you draw a conclusion from this. And it's kind of a one-shot thing. If you're data mining, find something, you draw the conclusion, you don't have to repeat and look for a new hypothesis. You're forming your hypothesis based on the data, as opposed to forming it based on some kind of loose idea of the physical world, and then gathering data. And so this has really been changing the way people have been doing science, especially in the last 10 years. And there's lots of technology that that we heard the previous speakers speak about that has really been that has really gone a long way to enabling this. One other thing I wanted to mention is it's important in this process is now every step along the way you start with noisy data, you're kind of squashing it down to a smaller subset, and then you're doing some mining, which maybe is there's some issues with forming hypothesis while checking they're statistically valid. There's kind of uncertainty and error in every step of these. And so it's important now to kind of understand this as you're going through this pipeline. Okay, and so I like to think of, you have some parameter that you quantify, and you can kind of push this parameter, how much resolution you have through towards your final answer at the end. And there are different trade-offs. And one of the big things that I'll talk a little bit more, which happens to be my area of research, is kind of looking at as you kind of get down to an important set of data and trade off the accuracy versus the size. If it's too big, it's hard to process. If it's too small, you've lost too much accuracy. And how do you understand this trade-off? And I'll try and go through some more examples. All right. So I'll come back to this a little bit later and talk about a specific part of this pipeline. But I also want to say, this analytics is this new thing that has been getting a lot of attention and interest. And why is this getting attention and interest now, right? Why didn't this happen, even as much 10 years ago when we're starting to change the way we're doing this data, we're starting to get a lot of it. And there's been kind of three parts that have kind of been building up towards it. The first part has been the changes in the systems, and so we heard some about this already. There are these new systems starting from MapReduce, and then Hadoop was a popular open source thing. A lot of that really spawned a lot of stuff in Silicon Valley. All these making data analytics possible for startups outside of Google. And then Spark has been this more recent thing, which has really massively sped this up. Uses some pretty cool insights. And one of the common thing which has kind of allowed each of these to make a step forward has been that they're looking at, so traditionally computer science algorithms, which is kind of my specialty, is designing ways to process something fast. And it's traditionally, you think of a computer as being kind of a disk which stores all your data, the memory which you can access very quickly, and then the processor which actually does stuff. And you count how many times you need to send something through the processor. That's how fast your algorithm takes. How many times you need to do a comparison or something like that. But as data got bigger, the first kind of change was that it wasn't the number of processor steps, it was how many times you need to go and get something from disk. When your data got bigger than your memory, you need to store it on, you couldn't just do it in memory, you need to do it on disk. Then this new change, so this had been around for a while. What's happened with these really big data is it didn't fit even on one machine, so you have this new barrier across the network between the machines. And so you need to organize how you design your algorithms to do this, and the systems that underlying can take advantage of these things by thinking how you communicate between these machines where you need to store all of your data. Okay. So this is kind of what has kind of pushed forward these different systems, which are now the backbone of being able to process this stuff. Okay. The next next interesting change is kind of these algorithms and these models that have gone with this. So there are the system changes. There are also then how we design things within these systems. And just kind of, I'll give you a small example here. So in some of these big companies on the internet, so probably this happens with Overstock, is that as they're getting, their data is not stored all on one computer, and in fact, when customers go to the website, maybe one computer can't handle all the customer traffic, right? So you're getting requests in from different customers, and they all get routed to a different computer, which is taking care of this. And you, as the user who's tracking all this information, you somehow want to get information from all these different computers as they're coming in. So you want to know that this, there's some chair being sold on Overstock right now, and it's very popular. We should maybe raise the price because we're going to sell them out for too cheap otherwise. And you want to know that as it's happening. So you somehow need to figure out when should you send an update to someone who's going to go and raise the price of this chair so that you can get more money because this all of a sudden was featured in like some TV show or something like that. Right? So you want to now, instead of figuring out how to do something like sorting in memory very quickly, you need to figure out how to communicate from many disparate distributed data sources to a single computer very quickly. Okay. So these are kind of new challenges which are coming up, which are very new research problems and are, I think, very quickly making their way into industry for these companies dealing with these big data. Okay. Another interesting phenomena is in how we've looked at the analysis of data. And there are certain things that we thought were true about various structures, such as which, when you got data very big, no longer held true. One example I like is when we start thinking about social networks. Okay, so if the people who worked in social networks maybe 15 years ago, maybe 20 years ago, were people who were in like a psychology department. And what they would do, and this is, they would go to like a high school, and they would go and see who had dated who in the high school, and they would get graphs like this. So the blue dots are the men, the pink dots are the females. You see who's dated who in there. And so you build a graph like this, and this is your social network. It's there may be a few hundred people here max, right? Because this would take weeks to gather all this data, right? And it's a few hundred, and they would study this, and they would try and cluster this graphs. They'd find these groups of people. They'd say, oh, there's this big cycle here. This is really big, interesting. Something's going on here. They'd draw the graph. You can draw it on the plane like this, and you can see everything that's going on. It was very clean. And then now we get these big social networks like Facebook, which is a billion people on it, and you have a relationship between who is friends with who, or there are more complex dynamics you can put in here. And your graphs, instead of these simple things that have nice clusterable regions and cycles you can see, they look like this, right? So there's this big hairball of data, and there's no good way of visualizing. At least the old techniques don't work anymore. When you try and find clusters in these graphs, you find one big cluster in the middle, right? And but this also seems very important. Now they were studying these high school dynamics. This really wasn't interesting to people. Now this has a lot of value in it, right? If Facebook, the way they can make money is they can advertise specifically to groups. They know a lot about you. So instead of having an ad on TV, which was going out to everyone and they thought this was going to get people to come into the store, they can target something specific to individuals because they know these people, they like sports and they also like hot pots, right? So that there's like a sports if there's a new sports and hot pot restaurant someplace, they would target it to specific people in the graph because they know that about them. And they would not just target maybe to anyone, but maybe certain people are very influential. You can find these structure in the graph where someone in the middle, like maybe here, this person kind of is a spoke, so there are lots of other people who are coming off of them. They must have a lot of influence of what's going on. You'd spend more to advertise on those people in this graph. And so Facebook has been trying to derive value from this, and they can drive tons and tons of value, right? They're like an immensely kind of highly valued company because they have all this information. And it's taken completely new techniques, a completely new way of understanding these structures at scale than what we knew about when they were much smaller. Okay, so these are kind of some new things that have been conceptually going on and changing that have been very exciting from the research area and from industry as well. Okay, so at this point I'm going to kind of drill down and talk about one specific application that I've worked on a little bit, and it's within this paradigm where you have a large data set and you want to kind of get kind of some summarization out of it, and I'll talk about a specific type of data, which is not like these social networks, is modeling data as a matrix. Okay, and I'll explain what this means and give some examples and how you would pull relevant information out of this matrix and how you can use this. And then the key challenge, because the data is so big, people have been doing this for 50 years from linear algebra, but the data always fit in the memory of the computer before. It no longer does that. So we need new algorithms in order to kind of update and analyze these matrices. Okay, so let's go through examples. So when I think of a matrix, it's just like it's kind of like a table in a database. So this, you can think of it as a rectangle, and then each cell in the rectangle is some piece of information. Okay, and I can't make it, to use this analysis, it can't be quite as general as a database, but I do have the similar thing that each row is, and each row kind of corresponds to one data point, so it's kind of a customer. Think of that, and each column is an attribute. But they should kind of all be, the quantities should all be roughly the same sort of thing. So I'll give some examples. One of the early ways people kind of use this properly for interesting data is they think of analyzing a bunch of some pictures or images, and so a picture is a bunch of pixels, right, at the lowest level, and they now have millions of pixels in them, and each pixel is corresponds to one column, and each row is one picture. Okay, and so what I've shown here is this example that was this cool idea, and there are other ways of doing these columns, but this is the simplest way. This is a cool example from what's called eigenfaces, and the idea was that so if you take a picture of someone and you rotate the camera a little bit, or you change the lighting condition, you're only changing a small number of parameters which describes the picture, but it has millions of these rows. So you want to somehow say, how do I describe some function which is kind of very simple just on these parameters which describes this data. And you can do some analysis of these taking a lot of these pictures, say the same person, different angles, different lighting conditions, and putting in a matrix, and then doing some matrix decomposition, and it will pull out the important features that captures all the information, because there's only a few parameters which controls how the camera or the lighting changes, even though the person is the same. Right? Okay. So another example is in text. So this is used on a lot of these search engines when they're trying to understand all these web pages. They'll look at the text on the web page, and they'll say, and I want to map each web page to a row in this matrix. And the idea is that what you do is you look at the individual words which are on the web page. This is one way of doing it. And for each word, you think of it as you keep a counter for how many times that word appears. And so there's a large number of words in the English language, but it's finite. I think it's between 10 and 100,000 something. So each of those could be a row. And so this will be zeros. Most of the words don't appear very often, but the words that do appear, you keep a count in the matrix for each document. And then you have this set of document, and you want to understand the set of topics which are in here. And the most basic way of doing this is called is called latent semantic indexing, and it basically is going to revolve down to a matrix operation once you store the data in this way. There are other ways like these topic models and so forth, which get used a lot in when you're making these recommendations for other web pages or other products based on the text that's included in there. A different way, again, I think I mentioned this, is if you have a big customer database, so all the users on a website, each customer is a row. Every column may be some transaction they did, or some specific sub-web page they looked at, or if they bought or they rated a product. Then this can be also captured in a matrix this way. And then in machine learning in general, you often get these data, and there's some abstract process which I won't describe, but you turn every data point into a bunch of these features, and each feature is a column, every data point is a row, and again maps to this matrix scenario. So the point of all this, I hope I give you some examples, maybe you can kind of understand, but there's a lot of type of data out there on the web that maps to some representation as a matrix, and it turns out for each one of these, the goal tends to be something like finding what's called a low rank approximation, and it corresponds to, in linear algebra, what you call singular value decomposition, or in some other places is called principal component analysis. Okay, so these are kind of these terms and they mean finding the important parts of a matrix. It's a linear subspace of the matrix, or a low rank approximation, if you know this. And I'll just a little bit of math just to show you. You have a matrix here. You break it into these parts. These product of three matrices. This one essentially tells you how important each part is, and this one tells you the description of the important parts. And it's this matrix operation. If you've taken linear algebra, you've probably learned about this singular value decomposition. And so the goal is going to be to compute these two matrices. These tell you what you need to know, summarizing the most important part of your data, called the singular values and singular vectors. And so the problem now is that this matrix of data you're storing doesn't fit on one machine. This is all of your customers. This is all the web pages. And so you store them on these big servers, and you want to compute these summaries so you can understand it and process it. Right? And so what you're doing is you're trying to turn this matrix into the smaller one, which is the product of these two matrices, the important parts of them. And this takes, what we say in algorithm, which generally takes n times d squared if you have n rows and d columns. The problem is n could be like something like 100 million, and d would be something like 10,000. Right? These may be numbers you would see. And so just reading this data would take may take a few days. And reading it would be n times d, and that'd be doing it distributed way. But now we need to do n times d squared, so 10,000 times as long to read it, which already took a day. So this is not possible to do. And the algorithms are generally assume everything's in memory, so it's even worse than this. So you can no longer create this really nice summary which captures what you want of your data using these old techniques, because your data is just so big. So you need to design these new algorithms in order to process this data and come up with these traditional summaries that we've known about for a while and have been useful, but now that the data is big, the way we think about this needs to change. Okay, so I won't get into too much of the detail. I worked mainly on one approach, and to kind of give you just a very high-level view of how it works is you can kind of think of doing this, what's called a stream, where one row is coming in at a time. And what you do is you have a summary, and you add one row to it, and you then update the summary, and you've increased the size by adding the row, and then you reduce the size back down again. And if you just do this naively, you can kind of run into some problems, so you need to there's some details under the hood here, but you can kind of always maintain a small summary, and then you can do these processes in parallel and then merge them together at the end. So you can kind of make this whole a very distributed process. And so you need to think about it now at the very large scale with these distributed settings that I had mentioned before. But there's new challenges because of this large data to do analysis. We kind of knew how to do, but you have to rethink a lot of these processes. Okay, so that was kind of this deep dive into here, and so I want to conclude now and leave time for questions by starting with a few overall view, a few questions myself. Okay, so telling you, we've come and learned a lot about how to deal with big data in the last 10 years, but there's some still new and pressing questions that I think are going to really. I think people are just starting to understand that these questions themselves are important. We haven't figured out how to deal with them at like very little at this point at all. So let me go through these. So if we get really good at finding these patterns in data, and we have lots of people using computers looking for them, will we find patterns that aren't really there, right? So if you randomly throw down data, an example I like is there's something that's called the birthday paradox, where if you have at least 23 people in a room together, there's at least 50% probability to have the same birthday, right? You might not expect that. There are 365 days in the year, but that two would have the same birthday with only 23 people might be unexpected. Now that's not some phenomena, that's not something interesting that happened, that's just random processes because of the number of possible collisions you can have. And so if we can find these patterns, how do we know that they really exist? And this happens in science a lot. There's been a number of papers that have been published in, say, Science and Nature that have people analyzed data, found some very small p-value, and then later discovered it was just some random process that they happened to it was a very small probability event that they happened to see. And things have to get retracted. So how do you deal with this? And this is becoming more and more of a problem. Another issue that's really been facing people is how can you do this analysis without really violating people's privacy? What is the line you can get? How much can you some people are complaining that all their data is becoming online, you're knowing too much about you. What is the right line there? And if we build new laws and legislation against this, is this going to ruin these companies that their whole valuation, like Facebook, is being able to do this analysis on people to serve ads? What is the right line here, and how are we going to deal with this? And then, finally, we're going to get more sources of data, and you may get multiple sources that tell you two different answers to the data. How do you differentiate these? Before, you didn't have so much data. You had one. You kind of trusted and went ahead with it, and maybe you're right, maybe you're wrong. But when you get so many conflicting sources, then what should you do? These are all questions that are, I believe, facing people, and academics are starting to look at this, and I think this is going to hit industry pretty quickly, and it's already affecting them in some ways as well. So great. So I'll stop here.
Thank you. Very expressive. I'm accurate guy was just different here between the traditional scientific research. So it may change my way to do my job. So any questions for Dr. Phillips? I have time for one quick question.
One more question. The data is so vast, not as fast as computer, but I think I/O is the main problem. How do you get in and get out fast?
Yeah.
That's the big problem.
Right. So as I said there, I/O is still a problem. And that comes in two places. How do you get data off of disk into the memory?
Right.
And how do you get data from I/O from one computer to another computer?
Exactly.
Right. And so this has kind of been this Spark system that was talked about earlier has been one of these big data systems that's trying to keep more and more data in memory. Actually, memory is getting a lot cheaper, so we're able to store more in it. The problem with Hadoop is that in order to deal with computers failing all the time, every time you did something, it wrote it back to disk in case the computer failed. And Spark kind of has a way around this. It can recover in ways without going back to disk. And so this has helped solve some of this I/O, but it's still a problem in some cases. And sometimes the solution is is designing algorithms. Sometimes it's buying more RAM in your computer.
So I do have a question. So I'm interested about your education program,
Yeah.
management, data management and analysis program.
Yeah.
So what's the requirement for getting into the program? Do you need very extensive programming experience or knowledge in order to get in there?
So we're a computer science department, and these are graduate programs. So most people come in with computer science background, but not all. So there are people who come in like so one of my students, John, so has more of a background in statistics, and some people with some quantitative background can pick up programming pretty quickly. And it's not all about programming. You need some, because to deal with data at scale, you're going to need to do some programming. So you may want to take a few classes in programming, and we have some in our department, introductory programming classes, and some people take those and get in. Other people have a little bit and then can jump right in. But you also need some math background to handle some of the math that goes into some of the analysis, or something quantitative.
Do you have a quick question? Okay.
Yeah, I wanted to Spark. One question is, I think when I working for I heard from the all Jupyter is cheaper compared to the interface. Now it's the Spark, you need the RAM. Actually, that makes it really expensive. And I understand the Spark you actually it's kind of like database you write a lot, so you don't need your packages. So what's the big difference here?
So what's the difference between Spark and
The
Hadoop, maybe? Is that
so
or between the traditional
I'm from the
database?
traditional database.
Yeah.
But when I see that you move from Hadoop to Spark to go around the problem of the
No, it's just a processing power. So it doesn't replace Hadoop itself. We're just trying to reduce the step for Hadoop MapReduce, because MapReduce is too slow. As Jeff just mentioned, you need to save data for every step of MapReduce. Save data back to HDFS, right? And in Spark, you don't need to do that. It supports distributed caching, so basically put all the data in memory if needed. So you can specify if you want to save that piece of data in memory, so that you can do lots of iterations. So it will speed up machine learning a lot. Yeah. So typically machine learning is about using the same data all over again, right? Lots of iterations.
So the big data many things actually you put the machine learning into different functions too.
No.
Parallel. You want the
So it's still distributed.
Sorry, it looks like you have a lot of detailed questions. So maybe you can talk about this afterwards. Okay. Thank you.